Okay, so today we'll talk about graphics pipeline in this lecture. So I will illustrate again all the more in details about all the steps of the graphics pipeline. Uh, we're not gonna have a programming session today because more or less I've shown you everybody everything what you need. So transformations, textures, mesh, lighting. So the next lecture I will do programming on shaders, right? Which is not mandatory for the project, but it's important that you know what is a shader. And the next lecture will have programming. This one we don't have, right? So this will be like illustrating the basic principles of the graphic pipeline, which is important you to understand how does it works. But first, let me remind you what we have talked in the what we have discussed last lecture. So last lecture we discussed about texture mapping, right? You remember that you have a 3D geometry, then you have so the principle is like you can put high resolution detail, colors, normal, bump mapping, like details on top of the geometry to increase the final realism of what you obtain. And yes, and this is more or less. Let me get my clock because I changed my laptop and I don't have the time here. Okay, and this is more or less the life cycle of a texture, right? We have discussed that you actually you load an image from a file, and this image is transformed into a format which is which is uncompressed, and it's much faster to read from the GPU and to do parallel computing in real time. We will see now how this works in the GPU and why we need parallel things, right? And what do you need for doing texture mapping? We have seen you need the UV mapping, right? Which is like a way to actually map each position, or each 3D position onto a 2D position on the texture space, okay? So if you don't have that, you cannot do texture mapping because you don't know how you actually can map the mesh onto the image, right? So this actually, it's usually one-to-one mapping, but it can be like several portions of the image, they map to the same portion of the geometry. Sorry, yes, sorry, different part of the geometry maps to same portion of the image if you have the same kind of detail there and there. But in general, texture mapping, UV mapping is the complex task that is usually demanded to artists, okay? When you actually program in Three.js, if you do a cube or if you do a sphere, implicit UV mapping is already into the framework, as we have seen, but if in general you load a mesh, when you're going to actually program your application or you're going out in industry and you're going to program in C++ application, you want to add textures, then you have to add UV mapping, right? Okay, so then we have seen how you can represent texture coordinates, okay? So you remember we have this structure of the mesh, index of vertices, like a vector of vertices with position plus a vector of triangles, right? And we have seen that actually when you flatten a mesh, you are actually specifying a UV mapping for each vertex, right? If you can flat each vertex of a triangle, then of course you can like map the whole triangle in UV space, okay? And here the idea is like you set UV for each vertex, right? So you can flatten it. But this approach has some problem, right? So what is the problem is that if you can see here, right? So essentially this chart, it actually has some cuts, right? And it means essentially that the vertex that stays here, for example, around the cut, it can be mapped in two different portions of the UV mapping, right? Because it's a cut, so the vertex which lays on the cut will map to different portions of the UV mapping, right? You get this? Okay. So if you get this, you can understand that actually one UV per vertex is not enough, because a vertex can map to different portions. Can you imagine, like, if you have a box, right? You cut a box, so then the vertex which is, and then you flat the box, right, on the plane. So the vertex which actually, the points which actually lay precisely on the cut, right, they map on one point or on the other, even though when you actually reassemble the mesh, they're actually on the same position in 3D. So that's why we need per edge texture coordinates, right? Which is also the thing we have seen when I did my exercise. When I push like triple for each triangle, I push triple of UV. So UV for the first vertex of the first triangle, UV for the second vertex, and so on. So you replicate a lot of information, but this way you can actually represent cuts, okay? So this was, again, in the recap, and we have seen also that some of the textures, they have the details of the overall object, right? For example, here you have different textures for the eye, or for the mouth of the bunny, and so on, right? But the fur, it's more or less periodic, right? So what I mean is, like, you can actually create a texture what is called a tileable, right? The texture that sometimes you find online, and you can tile, and it seems like a pattern which repeats infinitely, right? Which is like the meaning of texture in general, right? It's this one. It's not like represent different kind of details. It's like doing some kind of periodic details on the surface, right? And so to do that, the only thing you need is like a small portion of the image, right? And then OpenGL has a way to tile it infinitely. Okay? We have seen that also we can add alpha channel to textures. That's used a lot in games, where you actually, for example, you want to represent this character here, and you see it as these parts of the tissues on the flag that are, you see here. So this part of the tissues are a bit cutted, right? And how you can represent with a mesh with low polygon? Okay, so the idea is, like, instead of having only RGB, you use also the alpha channel, right? So that this portion here, they become transparent, and you actually create details even if there is no details, right? Geometrically, right? You actually incrementing this kind of details on the surface, of course, up to a certain limit, right? You cannot do real 3D geometry details, but you can cut out parts of flat surface, what is called these alpha or cutout textures, right? Okay. We have seen also bump mapping, which is instead of in a texture like storing the color, we store like a height map, and then what you have is like this bump mapped version of the one which is only color. So of course you can do color plus bump map, okay, and that's it. So and then you actually increase the kind of detail that you perceive about the object, even though there is no geometric detail, right? It's only like illusion. And of course, instead of having a bump map, which is a gray level image, right? The gray level indicates the height the pixel should be, right, when you render. You can have also normal maps. So these are two techniques that are very used a lot in games, together with other techniques like specular maps that I didn't explain to you. And these, for example, normal maps that you maybe want to use in your application that I've shown you several times with the code. The idea is like in each point of the texture map, instead of storing color or storing an eye field, you store the normal, right? And you store the normal of the surface in RGB format, right? Essentially, when so the values goes between 0 and 255. So when it's 0, it's -1. When it's 255, it's 1, and you interpolate in between. This way you can actually express every possible vector up to integer approximation of this byte that you are using between 0 and 255. And then what you actually do is like you can express a lot of normals, right? That are so these are normals, right? And then when you attach this texture on this geometry, even though this geometry is very low resolution, right? So these normals, they are attached on the triangles, and the light interact with it. So we have seen the effect when at the lecture, and maybe if we have time, I'll show something also today about that. Okay, so this concludes a bit the recap of the last lecture. Of course, you have seen some other details about how to place cuts, how many cuts we need. So it's everything recorded on the lecture, and you can see it online. So what I'm going to show you now is something a bit about hardware, right? So sorry if there is a bit of Italian. That's from motherboard, right? It's scheda madre. So the thing is like what you have is like GPU, which is stands for graphics processing unit, and it's actually the part of the graphics board that do the whole computation, right? And it actually is not as generic as the CPU. It's very specific, and it does like a very specific set of operation. And in this operation is much faster than the CPU, right? You will see that the difference between CPU and GPU is like computationally, the GPU can be considered more powerful and more because it can work also in a massive parallel way. But on the other hand, it's less versatile than the CPU, right? Programming on the GPU, I mean, the instruction set is lower, and it's specifically designed for some set of instruction. You cannot use the GPU for a lot of different kind of application. When you will see, there is a lot of there is some research, and this is a very interesting thing. There is a lot of research on what is called a GPU, right? Which means general purpose GPU. So people actually realize that the GPU is very powerful, like computational engine, and not only for like rendering something, right? But you can use also for. So there's people that actually created clusters of GPU to like compute protein foldings, right, for biology, or perhaps I think somebody who did also for mining bitcoins, right? Because it's a very strong and cheap with respect to the CPU, right? So you can really put a lot of GPU in parallel and solve a lot of problems. The problem is like it's massively parallel and the instruction set is small, right? So you have to know how to program on it, right? And it's something that you cannot automatize. So it's essentially a pipeline architecture. So you will see that how the vertex, how the triangles will go through all of the pipeline, and given some set of triangles, how you can get a set of pixels on the screen. We already seen at the first lectures. Just as introduction, here I will actually explain you more in detail. Yeah, and essentially it's a single instruction multiple, I don't remember. Yeah, single instruction, multiple device, I think, right? SIMD is called. So, but essentially the thing is like, so the idea is like you have a set of, a small set of instruction, and you have a lot of small processing unity. So you divide the data into a lot of small units, and then you massively parallelize the computation. You will see later what does it means. And of course you have in the graphics card and GPU has its own memory, right? So with the level of caching and everything, like the CPU, right? This is essentially where textures stand, right? This is where actually when you sometimes create the geometry and send to the GPU, if you don't need to update, right, and you don't modify the geometry, and you actually only apply translation or rotation, this is where your geometry stays, right? So what Three.js do, it actually takes the geometry, it creates a buffer and send the buffer to the GPU, right? And the GPU stores this buffer of geometry there, okay? So when you actually say you modify the geometry and you say the vertex need update, the geometry is recomputed again, so this buffer, and this transfer again from the CPU to the GPU, okay? That's what happened. Of course, this doesn't happen when you translate a mesh, because you're only applying a matrix of transformation, which can be done, which is actually done exactly on the GPU, right? You don't need to transfer go and back. You only need to transform it. So let's see. Okay, you all know the main processors. It's like NVIDIA MTA and MDA, AMD. Sorry. So, and the thing is, like the old, even like this chip, they also now use it for the for PlayStation or Xbox, right? The console games. And they have a lot of computing power, like thousands of gigaflops, which means like the amount of floating point operation you can do per second, right? So, and as I said, what you need is like you need a high performance bus, right? So the bottleneck usually in a graphics application, usually, not always, but main bottleneck is how much you transfer from the CPU to the GPU. Once the things are on the GPU, usually rendering is very fast. But when you actually have to transfer back the information, then you need I mean, actually you need a lot of computational times. For example, let's say like you have your Unity framework, right? And I mean, it's not just rendering, right? In a game, you have a lot of other things that require GPU. For example, handling collisions, right, between objects, or like physical simulation of the object, right? Of course, you can do also on the GPU, but this is gonna be very, very specialized code, not very generic and difficult to program, because you actually have this processor which is massively parallel, right? So you have to do all the you have to put all the code for coordinating parallel process. I don't know if you have done a bit of parallel computing already, but yeah, the idea is like some of the things you do on the CPU, and other things mostly related to rendering you do on the GPU, and you try to actually minimize as much as possible the transfer between both, right, using this bus. So essentially, this is the main, this is the architecture of a personal computer with graphics board, right? So you have the CPU, which is on arithmetic logic unit. I don't know if you know a bit about that, if you have done some of these course, like architectures of hardware, like how a computer is represented. and essentially you have a RAM, right? CPU is have also its internal cache, but I'm not gonna show you here. And then you have the graphics board, which is connected to a main bus, right? And then, I mean, all the latency time happen here in between, right? When you actually have the things here, it's pretty much fast because this internal bus is very fast. So while this bus, it's a more generic one, it has to handle multiple things, it has to be like very generic because you actually design your motherboard for handling a lot of different devices, right? While this one is specified for the RAM and the GPU, right? You know that this is only for these two guys that want to communicate, while this one has to be more generic, right? So, and yeah, the evolution of the GPU, it's very impressive, right? You can say the computational power has the amount of gigaflops per second, right? So maybe you can notice that this graph is not a linear scale, right? Because this is 10 to the power of 2, right? And this is 10 to the power of 3. So if this is 0, right? This should be, so 10 to the power of 3 is 10 times to 10 to the power of 2, right? So if you map this linear, right, this should go, I don't know, like out of the, you know what I'm saying? Okay, so this is called a logarithmic scale, otherwise you cannot see the progress. So I mean, so this is actually, it seems like linear, but it's not, because the scale it's logarithmic, right? And you can see how, I mean, here you have 10 to times 10 to the power of 4, right? For radian, right? Which is much more better than 10 to the power of 3. It's 10 times. And yes, that was for single precision, for floating operation. That is for double operation, more or less is the same. Like it's CPU versus GPU, right? So you can see, like, even if the GPU is cheaper, it has much more powerful in terms of computational power, right? The problem is, like, it's highly specialized, right? You cannot use as the CPU for every kind of computation or every kind of program you want to do. And here it is also the amount of processing elements, right? So because the GPU is designed to be massively parallel, right? And composed by, as I said, a set of reduced specialized instructions. And so this implies a set of reduced small processing units that are very cheap to replicate and to put on the same unit, right? So it's like small unit, like all together, right? While the CPU, essentially, you have more generic like processing units, but the degree of parallelism is small, right? Here you can see, like, how many parallel processing units you have in a GeForce, which is like more than 10 to the power of 3 with respect to, like, the cores of some CPU, which is 10, for example, right? And here it's like, you can see, like, that the amount of also, for example, resources, right, that you use is different, the way you distribute the resources. Because you have a lot of small processing unit, in the CPU you actually try to have less computational power, but more control and flexibility on what you are doing. So in the CPU, what is actually you are trying to control, like the parallelism and how the operation are performed on hardware, because it has to be very generic. while on the GPU more like the resources are dedicated more on the computational power, and the control it's smaller because I mean it's usually when you render, right, you don't need any control on how the parallelism of the rendering is performed. So this is the main thing, right? So let's do everything in parallel, per triangle in parallel, per vertex in parallel, per pixel in parallel, okay? We will see now that, of course, the advantage is the efficiency, as I said. You have, but it's the drawback is that the architecture is pretty rigid, right? As I said, like the amount of instruction, the amount of things you have to do, it's very specific, and yes, and in this sense, you can actually, if you want to use the GPU to do the same thing that you do on the CPU, you will need a lot of code to control like the parallelism, right? So I can make a simple example. Let's say like you do a program to simulate, I don't know, like to simulate a tissue, right, the forms, right? So if you do on the CPU, you can pass over all the vertices, for example, read the position of the vertex, compute a function, and then update the position of the vertex, let's say, right? On the GPU, if you do parallel on each vertex, where you actually read the position of the vertex, it can be already changed by the other process that in parallel is going to write on the neighboring vertex. So let's say like the position of the vertex is function of its neighbors. The position of a particle. I have a set of particles connected by string. Simple, right? The position of the particle is a function of the position of the neighbors. Okay? So if I do it in a sequential way, that's pretty easy, right? But if I do it in a parallel way, so that's possible that some process is going to write the position of the neighbors before I read the position at correct time, right? So I have to, or maybe some processes reading while the others are writing, right? And we suppose that the reading to happens before the writing of the second step, right? And you don't have this kind of control for free on the GPU because they don't put like hardware for control because you don't need for graphics. But if you can do, then it's gonna be a very like powerful computational unit. Okay, let's see how this kind of architecture is implemented in our paradigm, right? So why we need so the rasterization, why we need this, why it is important in the rasterization based hardware, right? So you remember we have several stages of our pipeline, and the main scope is to like render or to bring a 3D scene on the screen, right? So then to illuminate some pixel of some given color, and of course we already say that geometry is an abstract concept. So you have a set of points or lines, but mostly you have triangles, right? And then in the end, what you're going to get, so these are rendering primitives, and what you want to get is at the end you want to render them on screen, right? And the first part is, I will say, it's like transform, distress the object depending on the camera on the screen space, right? So then like transform to the screen, projecting, do the like projection matrix to see if it's perspective or not, and then in the end apply also the lighting on it and define the color depending on the material, on the normal, and on the illumination environment. We have seen that. So we'll go, yeah, this is the thing, right? So it's basically two different phases. We'll see that they are not happening one after the other. They will happen through the whole pipeline. So the idea is like first you transform the coordinates, and the idea is like you want to show the triangles that are visible. You want to actually clip the triangles that are like occluded by other triangles, and in the end you want also to find the colors of these triangles, right? And we see also all the pipeline about that. Okay. Yes. Suppose actually the scene is made of 3D triangles. We already seen that, right? So you have coordinates per vertex in a reference frame, which is the one that is it's called the world space, right? And then it's where you place the camera, that you set up the camera. So we have seen that the pipeline, it used this different stage that I already discussed in details in I think the first lessons, second one maybe. So you express these triangles in object coordinates, okay, again, which is the coordinates where the model has created its object. Then you transform to world coordinates, which are like, let's say, I can transform, for example, an object that has the barycenter somewhere, and it's been modeled in a completely random position, and then I can transform it and bring it to 0, 0 in front of the camera, right? So that's what the modeling matrix do, right? You program a set of transformation, which can be also the identity, can be also nothing, right? Which actually, when you actually say my models.translation, my model.rotation, what they're actually doing is you are actually specifying which modeling matrix is for that object, right? And you transform object coordinates to world coordinates when you actually program in Three.js and you specify this affine transformation, if you remember what does it means. Okay? And then there is a second step which actually transform all the geometry in a reference frame which is on the camera. So you remember iPhone, right? Reference frame, like direction of view, point of view, and up vector. And then in the end you actually project it, right? You have another stage where it depends about if your scene is orthographic or perspective, and you get these clip coordinates, and finally you get your vertex to the screen space. We already seen this stage. Now we go to see some more detail. So the idea is like, and you will see also next lecture when I talk about shaders. So the idea here is like every of this transformation, it's done by multiplying like vertices by a matrix, right? You remember that vertices are essentially vectors in 3D, right? And then you transform into homogeneous coordinates adding 1 or 0 at the end, and you multiply by a 4x4 matrix which encode each one of these transformations. And consider that the good thing of the GPU is that actually you can transform each triangle independently. That's the key. You can transform each triangle independently, you can transform each vertex independently, and so what you can do? You can parallelize, right? So then the main task of the GPU is like to do all this matrix multiplication massively in parallel, right, to speed up the entire process. Okay, I want you to understand the graphics pipeline because it's a bit of important when you go out and you program shaders or you want to do like advanced things with graphics, right? Okay, so yeah, here it's a bit more detail. So you have the triangles on the screen, right? And then you actually have the triangle, on 3D space, which is transformed on triangle in the screen space, and then then you actually have to find the algorithm how to find these pixels, and then you can process the pixels. So, and this is where the matrix are applied. Model view, the viewport, the view matrix, this one. So this transform object space to world space. This transform world space to viewport. This project to the clip coordinates, and this one project on the screen. So in the end, you have a final matrix that takes these clip coordinates and tells you which pixel of the screen you have to illuminate, right? and then of course which color. So which color we can compute, how we can compute the color. You remember where we can compute the lighting? There are two possibilities, right? There is Gouraud shading and Phong shading, right? One possibility is like compute the lighting in parallel here for each vertex, and then the color, and then let just simply interpolate the color here. The other possibility is like interpolate normals here, then I have one normal per pixel here, right? And I do the lighting at the last stage. Okay, you remember that? I hope so. If you don't remember, look at the slides. Do you understand that? Yes? No? Okay, good. Okay, so yes, you transform to the triangles, then you raster, and then you actually try to find which pixels are illuminated, and what you get is called pixel, but usually these are called fragments, right? Because you don't have only colors for that. Sometimes you have normal for the Phong shading. Sometimes you may have texture coordinates interpolated within the triangle, right? And then you have to go to the texture memory to get the color from the texture. So remember, like, imagine like here we have some texture coordinates, right? And you interpolate this one here inside, and then for each one of these you will have texture coordinates. Then the CPU, what it does, it accesses to the memory in the GPU and find the color of the texture relative to the texture coordinates, which is different from the one from the vertices, right? It's just a linear interpolation. We will see that later, next lecture when we talk about shaders. Okay, then we have final pixels. So as I said, lighting can be done in the transform phase or in the fragment process, right? So in the lighting, it's let me remind you, is the amount of light which determines also the color of an object hitting a particular portion of the surface, which depends by the position of the light, by the material properties, and by the normal of such position, right? The normal is important. What you can do is like you can compute per vertex and interpolate the lighting, the color, simple, or you can interpolate the normal and defer the lighting per fragments, and we will see next time. Okay, so then here it comes the parallelism, right? So each, the first part, when you actually transform, so the first part of the pipeline that takes like 3D object and put on the screen coordinates, right? It's parallel degrees. It depends by the amount of vertices, because what you are processing there is vertex, right? Okay, so you take, I mean, the geometry may be like 4 vertices, or it may be a big, let's say like it's a big quad of 2 triangles, right? So, and then, I mean, here it's very fast, right? In this sense, because it's just 4 vertices, right? But then maybe if this quad is big on the screen, it generates a lot of pixels, right? If you have a texture, then it generates a lot of pixels. And then you will, when you rasterize, so rasterize means take the 2D object and decide which pixel illuminate, okay? Then this will generate a lot of pixels and will be much more heavier for the final fragment process, right? On other hand, suppose you have a sphere or you have a model that you see very from far away, right? And you actually have, I don't know, you have, this model is very detailed, right? But because if you see from far away, you have a lot of vertices, so this face is gonna be really heavy, right? But it illuminates a small portion of pixels on the screen because you very see from far away, right? So then this will be much more heavy than this other face, right? So it doesn't, so number of primitives and number of pixels may be unrelated. Usually number of pixels are bigger than number of fragments are bigger than number of vertices, but if you do things well, that's the case, right? Because if you put textures or if you put bump mapping, you don't need a lot of vertices to encode details, right? So in games, usually number of fragments is bigger, and that's why the main concentration of parallelism is concentrated on the modern GPU. And yeah, as I said before, there are several bottlenecks when you program a graphics application. It can be like in the geometric subsystem, so how you transform the geometry on everything. It can be, usually it's on the bus. So usually it's how many things you transfer forth and back on the GPU. That's the main thing. And also it can be like how you compute things on the GPU, on the CPU. So suppose you have your game environment, right? You have to handle control, you have to handle physics and everything. Maybe that the bottleneck is not graphics, right? It's mostly the case for modern games, right? You have skinning, you have animations, you have to handle like new things that appear during the games. You have a lot of CPU things to handle. It's not just graphics, right? So you have to understand actually what is the bottleneck. Okay. As I say, here you do computation per vertex, right? Then you rasterize, and then you do computation per fragment. So it's important that since it's massively parallel, the more you can actually put like processing unit in the graphics pipeline, the more potential of computational power you get in this sense. And of course, the idea is like, okay, so GPU is made of a lot of simple components replicated a lot, and that are very cheap, much cheaper than CPU. How we can, that's why the secret, because it's becoming so much and much powerful, right? Because you have something that it's cost effective, right? And it's massively parallel. So how you can double the computational power? Simply doubling the processing unit, right? You have double the price, maybe, or less, but you get, I mean, it scales very well in this sense, because you just replicate these things, and you don't have to like design a new architecture like happened in the GPU. The only problem you have is a problem of space, physical space, and heating problems, right? Because you put a lot of components, so it's you always see in the GPU and graphics card these huge fans trying to. Okay. Yeah, we have seen that, right? This is the pipeline for a triangle. We have seen that. So essentially you have vertices, 3 vertices for each triangle. Then you have 3 projected vertices when you are in screen space, are 2D coordinates. And then you have pixels. The same thing you can do for lines. And you can find the amount of pixels and illuminate, or for points, okay? So it's kind of the same pipeline. Okay, so here is just to do a bit of recap about what's happening in the GPU. Massively parallelism of vertices, geometric primitives in general in the first phase, right? Each primitive is vertex treated independently by the others, so they can also arrive in the stage of the pipeline in different order, but in the end they will go through the whole pipeline, right? So these vertex, these triangles, they generate pixels, they illuminate pixels, right? When you have the pixels, then second stage, a lot of units that process the pixels in parallel and determine the colors, determine whatever things like textures and all the things that are interpolated within each texture, okay? And again, each fragment, its pixels, when I say pixels, is fragment is the same thing, right? It's a fragment is a pixel with additional information, is processed independently, right? And of course, you put the pixel on the screen buffer, and then the screen shows the screen buffer. Okay, So if you remember, we explained about Gouraud shading and Funk shading. So to give you the idea of how this works again, is like with Gouraud shading, you actually have, you send the vertices with property of the materials, and then here you compute the lighting, right? You compute the lighting means like depending on the normal, depending on the dot product, on the angle, right? Between the normal on the surface and the rays on incident lights, you find the amount of lights going for each vertex, right? And then you actually find a vertex here in parallel, which includes also the color of the vertex, because the color of the vertex is determined by the lighting, which has been already computed, right? And then this one will actually, when you have vertex of different colors, you project on screen, and they will generate a sort of fragments, and for each fragments you only have to interpolate the colors from the vertices, right? You will have a smooth transitions on the colors within the each pixel here, right? So this pixel here will have the color which has been interpolated by these ones, the colors of this one, right? And this is Gouraud shading, again, we already seen. And the result is much better than having like the same lighting for each phase, right? We have already seen that. And then there is a Funk shading, which has actually, it's a bit different. You have to interpolate the normal in the first stage, and then actually apply the lighting at the very end, okay? So the idea is like here you have, you pass vertices with normals, then you transform normal and position in screen space, and then you actually have, for each point, for each fragments, right, you have actually you transform the normal for each vertex in screen space, and then you interpolate the normal, right? And then you have the normal interpolated within this triangle in screen space, right? Already transformed and projected. And then what you have to do is like, when you have an interpolated normal for each vertex, you have actually, in the end, you have to do your computation of lighting per fragment, right? So again, you will have a normal per vertex, you transform it at this time, right? You don't compute the lighting here, you just transform it, and then you have a transformed position for each vertex, and then what is interpolated is the normal, not the color, right? And then at the very last stage, you have this triangle with a normal within the triangle, which resemble like a curved triangle, and then you apply the lighting for each fragment. Okay, and of course the results are a bit better, right? But it's more expensive. It's more independent of the tessellation. Okay, let's see now some more detail about how you rasterize things, right? We have seen how to transform. We have seen on the first lectures, right? What are the matrix? Now let's see how we rasterize. So how we, given the geometric primitives on screen space, we decide which pixel to illuminate. So the idea is like if you have a point here, right, in screen space, and you actually want to find the nearest pixel to this point to illuminate it, right? Because you know your screen, it's a discrete setting, right? You have a discrete set of pixels, and if those are float coordinates, you have to snap to certain integer to create your image, right? So that's why the screen with high resolution are better, because you don't see the artifacts. They approximate better the continuous image. So for a point, it's easy, right? You just take the closest coordinates and you round it, right? What about lines? So do you have an idea about how would you do that for these lines? So, come on. Yeah. Yeah, indeed, it's you are pretty close, but with a small variation, right? Yeah, the idea is like you can do so, right? Get the one closest pixel close to the polyline, right? And this pretty much work. But if you want, I mean, to have these fragments as straight as possible, maybe you can do something better. So the idea is like to see how much this line is horizontal or vertical, right? It's if you know the equation of a line, it's y equals ab plus some offset, right? If a is bigger than 0, that means like the line is mostly vertical. If a is so bigger than 1, sorry. If a is smaller than 1, that means the y it increases less than the x, right? So it's mostly horizontal. So the idea is this case is like, okay, let's say like a is smaller than 0, and indeed this line is more horizontal than vertical, because you can see if you count the number of pixels you in the horizontal, in the x direction is 9, while in the y is 7, right? So this a it should be less than 1 when you say like y equals to ax. If it's 1, it's going to be 45 degrees, right? That's pretty much clear. And then in this case, it's like, okay, so what you can do is like, if a is smaller than 1, it's mostly evolving along this direction. What you can do is like, you can like try to illuminate 1 pixel per each column, right? And then snap to the closest one. So in this sense, it tends to create things that resemble a bit more like a line. And on the other hand, if you have something which is like a slope, right? So something which is very almost vertical, and so the idea here. So can you imagine, like, if you do the same for this one? So we will have a pixel here, then a pixel here, then a pixel somewhere here, and then a pixel here. It's going to be 4 pixels, right? So it's incorrect. So in this case, what you have to do is consider instead rows, right? Because it's mostly vertical. And this is what you can do, right? Which is much better, okay? This is how you rasterize lines. Yes, so this is based on the analytic formulation of a line. So this a here, it controls how much y changes in function of x, right? Maybe thinks you have done this at some basic math course, right? And in the end is determine how much the line is vertical or horizontal, okay? So for example, if this one is 9 and this is 7, okay, m it's 7 over 9. It's m, it's like a here, okay? Okay, so then when you have to rasterize from one point to another, so first you have to compute a and b of this equation, right? And then see if you have to increment by the row and by the column, and then you have to, if you have to increment by the column, you increase y, and then you round it, and then you produce the fragment, and then you increase x. You find y, and then you increase x. So the idea is like that. Sorry. So you decide if you want to like cycle over the rows, so sorry, over the columns, as in this case. So you increment x, right? Or you have to increment y, and you cycle over the rows. And this depends about a, right? As I explained it before. yeah, this is how the algorithm works. Tack, and you round. Tack, and you round. You find the intersection and you round. Find the intersection and you round. And you do for each column, because mostly the line is more horizontal than vertical. Okay? What if you want to increase the thickness of the line? Actually, yes, you simply put one pixel above and one pixel below, right? Given the direction of the line. Okay? Simple. Yeah, this is the other case when you actually have a line which is mostly vertical than horizontal, so the thickness, it evolves on the horizontal thing. So I hope these drawings help you to understand, okay? Because without drawings it's impossible. It takes a lot of time to do all these diagrams, but yeah, trying to do the best, and I think it's hope it's more, you can understand better. Of course, this is just an approximation, right? I mean, if you have a very if you have a line which is like oriented along the axis, right? This is perfect, okay? Because you have one pixel there, one pixel there. But if you have something like this, right? Maybe you would like to have something here and something here, right? But you don't have the pixel, right? So that will go like this, right? And remember that has to be done in parallel. It has to be efficient. So you may not want to go to do something very complicated, because otherwise it's actually slow the entire process. What you can do is like you can add the anti-aliasing. So aliasing it's exactly this error, right? When you actually pass from a continuous representation, for example, of a line, to a digital discretized representation, which are the pixels on the screen. So you commit this error, right? And sometimes you can perceive that error, right? It depends, it's also about how much pixels or the resolution of the screen. But you may need something which is called anti-aliasing, right? So sometimes what you can do is like you can imagine to have your screen double the size, and then you actually reduce it by undersampling. And this is actually how it does anti-aliasing, right? It's usually you imagine like your screen has a double resolution, you rasterize your line on a double resolution, and of course you have to double also the thickness, right? And all the things are doubled. So you imagine to have like double number of pixels, and then you downsample as you downsample an image, right? So what happens if you have some pixels that are blurred in between, right? This is how anti-aliasing works. And in the end, this gives a much better perceptive qualities of the lines. So you can go from the one on the left to the one on the right. I mean, here, if you program it, you can see that it works when you actually draw lines, right? This is how anti-aliasing works. Okay. Now we have seen how to raster points, how to rasterize lines. So let's try to see how to rasterize triangles, right? Okay. So here, the idea is like, suppose you have this triangle, right, in 2D, and this is your screen space. So these are the pixels that has to be illuminated. So the idea is to scan every line. So you sort by Y, and then you scan a line, and then you find the first fragments that fall in, and the first fragment fall out. And of course, since it's a triangle, right? Since it's a concave, it's convex shape, right? What happens is like if this fall in, right, and the other fall out, so what's in between should necessarily fall in, right? If this was a concave shape, that would be different, because then it's like here you can imagine having some primitives that goes like this, like let's say like, I don't know, a quad, right? You add the vertex here, right? And this goes like this. So then, I mean, you have in, out, but because it's convex, never happens, right? So then you actually produce the fragments in between, okay, in parallel, okay? And then you can do actually this one for every scan line in parallel, and of course parallelize it with respect to everything, okay? So, but yeah, how we can, I mean, it's, so far what I described is like to produce one fragment at a time, right? So to parallelize, you can actually groups fragments in, of course, this is for one triangle, right? Imagine that you do this in parallel per triangle, right? So this is already a first degree of parallelism. But if you want to even parallelize more, you can group pixels in groups, like 2 by 2, 4 by 4, or 8 by 1, it depends. And then you actually like compute all of them and see, I mean, if all of them, they fall outside, you discard them. If they are partially inside or partially outside, then you actually go and see which are the inside and what are the outside, right? You can try to jump bigger jumps. Okay, but so it's important that you understand what is the main idea behind that, right? And of course, you don't have to scan all the pixels of your screen for a given triangle, right? Because it's overshooting. So what you can do is like, you first compute the bounding box of your triangles. So bounding box in 2D, it's an axis-aligned bounding box which contains axis-aligned box which contains your geometric primitives, in this case the triangle, and then you do the scan line only on this, right? You round to integer, for example, like this, and then you make it, for example, divisible by 2, so then you can group into 4 by 4, okay, if you want to add some degrees of parallelism, and then you can process each pixel block and then see in parallel which are inside and which are outside, right? So these are like partially outside and partially inside, okay? So the first one, it's like I process all of them, right? And then there are 2 inside and 2 outside. Then this other one, I process all of them, there is 1 inside. These all together are outside, and then if all together are outside, all the rest will be outside, okay? But then you increase by 4 by just parallelizing instead of doing pixel by pixel, okay? The same algorithm, but instead of looking 1 pixel at a time, you look group of pixels. And of course, this box has to be I mean, you should be able to divide by the kernel of pixel you use it. Okay. Okay, what do you need now to rasterize? So you need how to do the algorithm. What do you actually need? You need a way to establish if a point falls inside or outside a triangle, right? You need a strategy very fast to understand that, right? So how you do that? So the idea is like in 2D, right? Let's say like we already, so forget about 3D. We rasterized things. We are in the view of the camera. We also applied our projection matrix. We have like orthographic or like perspective things, and the things are on clip coordinates on the screen, right? So forget about 3D. 2D, easy. Okay, what is a triangle? What is the set of points inside the triangles? So the idea is like you can imagine to have 3 different lines, right? And each lines have a normal here as a vector tangent. And you can say, okay, so the point inside the triangle are all the points which are on this side of this one, on this side of this one, on this side of this one. So let me make myself more clear. So I get this line, and this line, it actually discard. So if I say I'm on the right side of this line, so opposite to the tangent, and of course you say no for this one, right? And you say yes for, so this one are in this hemispace, right? Half parts of the space, of the 2D space. Then you get this other one, and you say no, yes, yes, and then you get this other one, yes, okay. So what is the portion of space that has 3 yes? The only one inside the triangle, right? It's pretty easy. And the direction of this tangent line is uniquely determined by how you actually put the sense of rotation of these triangles, right? So if you actually have this plus this plus this plus this, so these normals, they always point outside this direction, right? Okay. Good. If you actually specify the other way, it should be in the other direction. So the face is flipped in the other direction. But you will see later on how to discard these situations. Okay, so then for each fragment, what you have to do, for each fragment, you know which triangles you come from, right? You need the edges, and then you have to understand for each triangle, for each edge, if it's fall inside or outside, right? On which part of the hemisphere of the half space it fall. So, and then you actually, for each fragment, you have 3 answers, and then you actually have to implement this test, as I say, right? So, and if the fragment is outside, you mark it as outside in your rasterization. Otherwise, you illuminate the fragment. And yes, so the idea is like this is the edge of the triangle, right? And what is the test that you understand if this point is aligned with this or not? You remember it's dot product, right? Dot product, as we've shown, let me, I have not the slide here, but if you remember, dot product, when 2 vectors are along the same direction, it's positive, right? When 2 vectors become orthogonal, it's 0. When it goes on the other side, it becomes negative, right? This is dot product is used for lighting, and it's used when you have to understand if 2 vectors are on the same semi-space with respect to the tangent plane of that vectors. So, and then what you have to do in this case, you have to take this line and take the dot product of Q. I don't know what happened there. I hope you can see here. But the screen is not working anymore. Okay, so this is the test, right? You have this line, right? You get this vector, which is Q minus P, right? And then you multiply by N. Multiply means dot product, okay? If the dot product is positive, they lying on the same hemispace. If the dot product is negative, so it lies on the other side. So yes, in this case, for example, the dot product with this yes. So here we have this normal. Here, sorry. Here I think it's wrong. This direction should be on the other side. Yeah, anyway, I think you understand the fact, right? You have this line, you find this direction, which is the orthogonal one, and this is simply done by, for example, this direction, it can be like minus y1 minus y0, and on y you put x1 minus x0. You will see like if you have these two, and if you find this direction, you will have this orthogonal line, right, in 2D. if you take x and y, so these two vectors, and then you have another vector which is actually q minus v0, right? And then you actually do the dot product of q minus v0 times d, right? And this is, if it's positive, it's stay inside or it stay outside. So this should be opposite, yes or no. Okay, so other thing that we have to see is how to clip primitives, right? You remember that when you actually set the camera, you set a view volume, right? So a view volume, it's like you are actually setting what we say the frustum, right? So you set your camera, you say it also, usually it's one by one, but you can say like what is the angle of your camera, what is the x up and x down and the different frustum, and what is the nearest clipping plane and the farthest clipping plane. So in general what you have is like, let me see if I have here a slide, or maybe, yes, you remember this one, right? So you set your camera, right? You set the focal length, or you set the angle, and then you get near a far plane, and you have defined this view volume. So what you want to discard all the primitives that are outside of this view volume, right? You don't want to create fragments for the ones that are not there, because they obviously they will fall outside of the screen space. So what you can do is like, okay, so now that I explained everything, so it's like you have a screen, right? So maybe what you can do is like, okay, let's see if all the vertices fall outside, maybe you can cool, no problem, right? So if it's inside, you can rasterize. If it's partial, well, then you actually, what you can do, it's like you can try to find the intersections, right? This is the old school. This is how it was done before the modern GPU, right? And then you can try to triangulate it, right? And then rasterize these triangles. So things may be more complicated. When you actually have much complex shapes, then you have to find multiple intersections and triangulate and rasterize here. So this slows down everything. So even in this case, it's even more complicated because you have 3 points that falls outside of the viewport, but you actually, part of the triangle is inside. So this becomes very complicated, right? You have to triangulate like this, and I mean, it's getting more complicated, right? So what instead you do now, you actually find the bounding box, and then you demand this on the, I mean, if the whole bounding box fall outside, you don't rasterize. Otherwise, what you do is you get the bounding box of your object, right, before in the screen space, and you actually intersect the bounding box with the bounding box of the screen. And then you process in parallel these fragments, right? And you rasterize only in the intersection, and you discard all the fragments that falls outside of the intersection. And this is very simple, and because of the parallelism, this is much more powerful than the other. And of course, there is no way to fail. It's simple, right? And simplicity is the, how they say, is the best sophistication, right? I don't know how you can say. It's the most genius thing, right? Sometimes when it works. Okay. And what about the other that falls outside the far planes? Well, then you can discard them looking at the depth of each fragment, right? So each fragment has a depth. If the depth is bigger than the one that you specified, you just discard it. Okay? Okay. You have a bit of overhead because you have to do some, maybe you have to do some intersection, like test inside outside for a lot of fragments that you maybe don't need, but it's very parallel and it's easy to assemble this kind of process, right? Okay, so And this is a very nasty case, right? So for example, suppose you have these triangles like this that falls in the screen. What happens? It happens that the bounding box is the entire screen, right? The intersection of the bounding box is the entire screen. And then what you have to do is like you have to just check check the inside-outside test with all the points, and that's a very bad case, right? But I mean, come on. Usually it performs very bad. Another thing we want to do is like to discard the face that you see, like back face culling, what is called a back face culling. When you actually in 3JS you put your geometry your material dot side, it can be like single side or double side. When you put single side, by default, it's not double, it discards all the elements whose normal is the dot product of the view direction with respect to the normal of the surface. It's the same. It's bigger than 1, right? So this one is the one that you can see, right? Because this is the direction, and the direction of the surface is opposite. So the dot product is less than 1, right? These one are coherent, and you are seeing from the inside. So you don't want to render it, right? If you put single side. If you put double side, yes. So you just put an ups and you on the direction of the normal on the dot product, and it's always positive. Yeah, this is easy. You just have to see the normals and multiply the normals by the view direction and discard all the fragments or the face directly, right? You discard face directly, whose per face normal is opposite to the view direction. Notice that here it's not the normal you specify, not the normal you give for rendering purpose. It's the normal that actually it computes the machine itself, given the 3 vertex, right? So you cannot specify these normals for clipping. The machine it computes by itself. It's not the one that you specify for rendering, right? That you can modify and do the FX. No, this is the real normal, computed arithmetically by the machine. Okay. Yeah, that I already explained you, right? That the normal on the face, it tells you what is the inside or the outside portion of the surface, right? And maybe you want to see that parts that are seen from inside, you put single size, you do like back face culling or not. It depends. How you compute the normal, you remember, right? You get a triangle, you get 2 vectors, you do the cross product, you get the normal, okay? So front face, right, is when the normal is parallel to it's opposite to the view direction. For example, let's see like you have a cup, right, with no thickness, right? I mean, if for each face of the cup you have the normal pointed outside, when you see a cup from inside, you see nothing. All the fragments are discarded because the outside part of this triangle point outside. If the cup is solid, right, then you have outside even when you see inside the cup, okay? Okay, when you actually do, you actually discard the triangle before you do the rasterization, right? You see if the normal with respect to the view direction is the same direction, means that you are seeing the face from the interior, you discard the entire triangle, you don't do the rasterization. Okay, so if you do like back face culling, right, you actually speed up the entire process because most of this face you will not see. If you have a closed surface, the idea is like if you have a closed surface, if you have a sphere, unless you move inside the sphere, you will never see that face. Because all the face, when you see, right, they will have the normal pointing in the direction opposite of the view direction. right? So the other face that in this sense they have their normal, like on the other side you can discard, right? And the gain in terms of performance is high, right? So double side, sometimes it makes things much slower because you have to process much triangles, right? And you create more fragments. Okay, as I said, it's OpenGL that understand the normal and understand which triangles to trim or which triangle to render. But sometimes it's not enough, right? Because you may have this kind of situation where you actually have phase and you have occlusions, right? So if you see this geometry, right, you have to understand that the green part, it occludes the yellow part, and like that. You cannot render like this, right? You have to understand which occludes which in order to show the right fragments. And to do so, there is several algorithms. For example, you can actually, this is what is called a hidden surface removal, right? If an object is not transparent, right, the objects that are far away, they are occluded by the objects that are closer. And one possibility is like, okay, I can shoot array finding which one occlude which, and maybe split each triangles with the other triangles with complex geometric operation and see which are occluded by other. That's impossible, right? I mean, you have a lot of remeshing, you have to split triangles when they intersect, makes no sense. So the other possibility is like to use the painter's algorithm, right? So the painter's algorithm is draw polygons from front to back. So you start with the background, then you draw the clouds, then you draw the mountains, then you draw the grass, and then the trees, right? And then the house, right? And the one that it's drawn last time wins, right? So in this sense, you actually sort your primitive from the last one to the first one, right? And then you start drawing from that. And the last one, it's always overwrite the fragments, the pixel of the one that comes before. Well, I mean, this works, but you require sorting the primitives, right? Which can be like n log n. It's not, you know that sorting algorithms are not linear, are super linear. And if you do like merge sorting or quick sort, if you do an algorithm, you see that it's n log n. And of course, I mean, the other problem is like a primitive, it doesn't have a single depth value. It can span over different depth value from the same point of view. And then you can, and then if you have to do that, first you have to do in the CPU. So you don't use any advantage of the parallelism of the GPU. And second, you have to do like you have to do a sorting before to drawing all the primitives, right? And then you have to see, okay, given the depth, so this object, it covers this range of depth, and then you have this other object that covers other range of depth, and then you have, I mean, if they cover different ranges, right, that intersect, how you draw them? I mean, it's difficult, right? If they have an intersection, what comes before the other? It depends. I mean, this one comes before the other here, this other one comes before the other in this other sense. And you cannot handle these kind of things, right? I mean, this one occlude this, that occlude this, that occlude that. I mean, this is just a simple algorithm that we have in mind, but sometimes, I mean, it's impractical, right? It's impractical. So how we can do then occlusion? You have an idea how you will do, like, how can you find occlusion? You can do per fragment, right? And exploit the parallelism of the GPU. Again, the painter algorithm supports also semi-transparent object, but it's very non-practical. So what is called is Z-buffer algorithm or depth buffer algorithm. So each pixel on the screen, it doesn't have only like X and Y on the screen, but it's only have like each fragments generated by each triangle has also a depth value, right? Depth value, you remember when we talk about clip coordinates, right? Clip coordinates in the screen space, let me remind you a bit. Yes, here, right? You don't have just in this reference frame, right? For each triangle, you don't have just the position of the vertices in 2D, right? But you have also the depth along this direction, along the view direction, right? And what are the one that you see before? The one that has lower depth, right? So when you actually rasterize, you also interpolate depth from the triangle vertices, and you have for each pixel of the screen space, for each fragment, so for each pixel generated by each triangle, not only the color but also the depth on the view volume, okay? And then the process will become much easier exploiting all this parallelism, because in the end what you have to do, let me come back to the slides. You have also not a screen buffer only, right, which tells you like the color of each texture. You have also a depth buffer, which stores for each primitive, for each pixel, the depth. And the idea is like, yes, depth for each pixel. And the idea is like, as I said before, after transform, you actually save the depth in the camera space, in the clip space for each vertex as an additional attribute, right? So each vertex not only have color and position in 2D, but it has also the depth, right? And then this depth, it's interpolated as the color and as the texture, similar way, okay? And then here, you actually have to, what you have to do is like when a new primitive arrives with a lower value of depth with respect to the camera, it wins, okay? So you actually have to do like that. So if for each fragment which has a depth that is smaller than the depth buffer, so you actually update the depth buffer, and then you set the color for this one, because this is one that is visible. Okay? Is it clear? So here we have an example. Yeah, this is called a depth test. Here you have an example. Suppose you have a primitive that set the depth to this value, right? Oh, this will be a floating point between 0 and 1. I put it this one for convenience, to make it easier to read for you, instead of like floating point between 0 and 1, which would be like crazy, right? Then I draw another, then it arrives another triangle which has this value of depth. What I do, it's at the result, it's this one, right? So that means that this primitive, it will be totally white and it has depth 63. Then it arrives a triangle that stays before that has depth 5 and color green. So I update the depth buffer to 5 and the color buffer to green, where it's actually win in the depth. Okay? And then if I add another triangle like this, right, which can have different depth, because, so the idea is like what I said, you have depth when you transform for each vertex. So here you have depth 2 and 7, here you have 2 and 7. So this is linearly interpolated inside the triangle for each fragment, okay? So if this 2 and this is 7, so you will have 2, 3, 4, 5, 6, right? That means that the triangle span depth along the view direction, okay? Do you understand that? Okay. And then if you sum up this mask, in the end you get something like this. So that means like a triangle is partially occluded by another, okay? And this is highly parallel, right? The only thing you have to check is that it never happens that two processes write at the depth buffer together, because writing has to be serialized, and also writing at the color buffer is the same. Yes, it works in all the cases, right? It doesn't matter if you have mutual independence or everything. It do operation for fragment, and it's it's done for our hardware, right? For our massively parallel hardware. Of course, as I said, it shares data in write and read. You have to be careful, right? So, I mean, it's ordered independent, right? Because the smallest one win. Yeah?
Are the depth values stored as whole digits or more as decimal points?
Decimal points. Yeah, decimal points between 0 and 1, because the clipping volume is between 0 and 1, but just for like illustration purpose, I put it as an integer, because otherwise it would be difficult to write decimal in these small boxes. But yeah, the idea is like works for totally opaque object, right? If you have transparent, it doesn't work anymore. Then it becomes more harder, right? And then you have to sort manually for. And then it share data in read and write, right? So when somebody read, you cannot write at the same time, because you can read rubbish and the same, right? The two things they cannot write at the same time. So you need some kind of lock for make the writing or reading like not happens two process writing or reading at the same pixel on the frame buffer, on the screen buffer, or the same pixel on the depth buffer. So this is mostly enough, everything. The only thing I want to show you is that this algorithm has another problem. You maybe noticed that you can have z-fighting, right? It happens when exactly two primitives are coincident, right? And you don't know which one is before the other, because they have the same value of z, right? And then what you get is random, right? You get this kind of fx, because they are the same depth with respect to the viewpoint. So sometimes some pixel win, sometimes other pixel win, depending on the approximation of the operation, right? It's totally chaotic. And also, for example, when you have this kind of fx, for example, let's say like you try to draw two different objects of two different colors, but they are coincident, right? So maybe this is the result of an object blue and an object white, and you have this fighting. So sometimes with the fragments we have white, sometimes with the fragment that have blue. It's not clear what happened, but it's only happen when you have coincident triangles, right, in 3D. Okay, so a bit of recap, and then we have finished for today. Next time we will see, I will do the programming, and I will show you some shaders, okay? Even though shaders are not required in the project, because it's a bit difficult. If you want to put it's a plus, but I will going to ask in the quiz a bit of the shaders as well. So today this was a bit long lecture, but I hope you actually understand how the graphics pipeline work in like an overview of how the graphics pipeline work, because it's important that you actually, if you program games, if you go outside, you know how the graphics pipeline works and why it's so efficient, right? So main difference: CPU, very flexible architecture, low degree of parallelism, like for algorithmic logic. GPU, like reduced set of instruction, no controls on parallelism, or at least less control on parallelism, a lot of small parallel processing unit, okay? This is again the pipeline. You take the object, you transform to the world coordinates, you apply your rotation on translation, as you see on 3JS, then you transform to the screen, then from the screen I transform it using orthographic or I don't remember. Orthographic or perspective, okay? Perspective projection, and you get your clip coordinates, and then finally you project to the screen space and you get your pixel. Okay, so we have two stages where things happen in parallel. You can do parallel per vertex, parallel per fragment. This will come up in two programs that you can write for shaders. You can write vertex shaders and fragment shaders that we'll see next lecture. Vertex shaders are a small program that operates for each vertex in parallel. Fragment shaders that are a small program that operates for each pixel in parallel, allows you to define your lighting strategy, right? If you don't want the one that OpenGL provides you. How you can rasterize a triangle? You find the bounding box, and then you group set of pixel. You find if it's find outside, inside. The first one, it falls all outside. It's all outside, right? You repeat the process. You rasterize your triangle. What you need the test for saying if a point is inside or outside of the triangle. We have seen how we do it. Okay? Other thing is like to discard the face that you see from the other side. For example, let's suppose this is a closed object, right? You don't want to see this face. First because are occluded by this, right? But instead of even processing the fragments, you can actually discard before, because you can actually say that this one, the outside of this object, is in this direction, which is coherent with the direction of view. It's not opposite, so you discard this triangle immediately on the first stage of the pipeline, and you don't even generate the fragments, right? So you gain a lot of speed up. Rastering is like how we handle depth between objects, so how we handle occlusion with the depth buffer, and we see like each primitive is right on top of the other. In the end, you have like depth and color per pixel, right? Yeah, and that's it. Sorry, it was a bit long, but now you can understand all the different stages, right? Now that we arrived.